Hello and welcome back to another video. So in the last one, we discussed the GTN model, its mathematics and its basic formulation, and we paved a way to couple GTN with the phase field model, which was our ultimate goal, right? So in this video, we will talk about coupling GTN with the phase field fracture, precisely how it runs in Abacus through a VUMAT and VHETVAL formulation. We will not discuss the code in this video, but then I'll give a basic algorithm and give a basic formulation on how it needs to run. So from damage model to a working simulation. So to recap, GTN tells us when and how much a material point is damaged through porosity F. So F was the void volume fraction or the porosity that we used to denote. But it deletes elements abruptly. It does not describe a smooth propagating crack. Okay. So what does GTN give us? GTN gives us a damage state F at every point. Okay. So essentially in every point in the domain, you will be able to know what is the porosity value. Correct? But it won't give us an actual crack path. Okay. So we still need a way to represent the crack itself. So this porosity contour will not give you the crack path. You will need a way to represent the crack itself. So a phase field model that smears the crack is kind of essential in order to get the crack path. So to recap the basic idea of a phase field, you can find it in my previous lectures. I had given a complete playlist of 3 videos explaining the phase field model and the entire mathematical formulation of it. So you are free to look into it. So I will just recap here. The idea of a phase field, instead of tracking a sharp crack surface, we introduce a smooth variable D. So you can represent phase field using this letter D or with the Greek letter phi. So this variable D, it goes from 0, which is intact, to 1, which is fully broken over a small width. And this width was characterized by, if you remember correctly, it was characterized by the length scale parameter LC. So if you have a sharp crack or a discontinuity in a body, the phase field, it replaces this sharp crack with a smeared band of width LC. Okay, so this smeared band, this contour is the phase field contour. Now we had this degradation function in order to degrade stress and the strain energy density. So this degradation function G of D was 1 minus D whole square plus some stability parameter kappa, which was very, very small. So this degradation function GD multiplies the stiffness. So as D rises, the material carries less and less load. Why? Because crack propagation is a stress releasing process. Okay. So this is how a phase field contour looks like. You can see this gradual decline from 1 to 0 characterized by this with LC. Okay. So if LC tends to 0, you get a sharp crack. You get a sharp crack. So this D will be 0. Now, the governing principle, energy, a crack forms when it is energetically favorable, which is understandable. The total energy balances stored elastic energy against the energy needed to create crack surface. So in order to conserve the Griffiths formulation, you have to have new surfaces whenever a crack propagates. So a crack propagating essentially is doing what? It is decreasing the strain energy density. But where will that energy go? That energy will go in creating new surfaces. Okay. So essentially we have the internal bulk energy functional as this. Okay, so this is the internal strain energy per unit volume multiplied by dV integrated over the domain plus the fracture energy, where Gc multiplied by small gamma was what? Small gamma was the crack surface energy density. Okay, and Gc is the critical energy release rate, which is a material parameter. So the crack surface density regularized over with Lc was defined as what? It was defined as this for multiple dimensions. So this was a function of Lc and phase field and also the gradient of phase field. So Lc is the length scale that sets the width of the smeared crack. Now, how does the crack evolve? The crack evolves by minimizing the energy, which gives the phase field evolution equation a balance of viscous, diffusion and driving terms. So this is the governing equation of the phase field model. If you remember correctly, in the previous video I had mentioned that we will be talking dynamic cases, because this GTN model is basically used for simulating high impact experiments and experiments involving very high velocity. So you cannot simulate them using static. You have to use dynamic. So essentially, by the same process how you derive the static phase field governing equation, you also derive the dynamic phase field governing equation, where this extra term comes. This extra term is eta d dot. So this d dot is what? D dot is the evolution of the phase field multiplied by a viscosity parameter eta. Okay, so this viscosity parameter does what? By multiplying this with the evolution, it actually hinders or it changes how fast the phase field crack grows. Okay, so if eta is high, that means you have a highly viscous material. Like it is not physical viscosity, it is the viscosity of the phase field contour itself, like how fast or slow it will diffuse into the main material. Okay, you should remember that this phase field evolution equation is actually a diffusion equation. Okay, so it is a diffusion equation, and if you insert viscosity in front of it, you essentially control how fast or slow the phase field contour is diffusing inside the main body. Okay, so you have this term eta d dot, which is the viscous regularization or the rate limiter. You have this term Lc square nabla square d, which is the diffusion term. It spreads the crack over with Lc. And you have this term, which is the evolution term or the driving term, because the driving force from the history field H is present. So this history field H is present, which is acting like the driving force of the phase field crack. Okay. Now we talk about the coupling. So we talk about how porosity is supposed to drive the crack. Okay, so this is the heart of the model. The GTN porosity F feeds the phase field history variable H. So in order to couple phase field with viscosity, you have to have a method to define the history field, because the history field is what drives the crack, right? So this history field, if you can define a function of porosity, you are done. Okay, so again I am repeating, if this history field is a function of porosity, you are basically done. You are basically done coupling porosity with phase field. Okay, so voids don't just weaken the point, they nucleate the crack. Okay, if you remember, in the previous video I talked about crack nucleation and how we are not considering them in the porosity growth equation, right? We will be considering nucleation of the crack through phase field. Okay, so this is how we take into account that voids grow and they nucleate in order to form the main crack. So there are many formulations recently that have been published regarding this coupling, but this is more of a recent work. So one such formulation I will discuss, which is this. Okay, so this is essentially the history field. The history field is what? Again, the history field, previously it was a function of the strain energy densities, psi 0 plus, psi 0 minus, and stuff like that. Okay, but now we define it like this. Okay, so maximum of this function, which is ff minus fc by ff minus f whole square minus 1. So essentially what? Essentially when f is less than fc, take into account these Macaulay brackets. So when f is less than fc, the history field is 0. Okay, so prior to critical porosity, when your initial porosity is growing from f0 to fc, you will not see any crack. Okay, you will not see any crack. But when f grows beyond fc, you will start seeing crack. Okay, so that is when the history field grows and the phase field eventually grows. Okay, so in the zone from fc to ff, your h will have a non-zero value, and thus your phi will have a non-zero value. But when f grows beyond ff, what happens? When f grows beyond ff, your history field is essentially infinite. Okay, so when f is equals to ff, your history field is essentially infinite. If you remember correctly, f cannot grow beyond ff. Okay, in most ideal scenarios, f cannot grow beyond ff. So when f is equals to ff, this history field is essentially infinite. And to prevent that infinite, in finite element software terms, we always use a cap in the history field while we write our code. Okay, so suppose you are not allowing the history field to increase beyond a certain constant value, say 50 or 100 or whatever your problem demands you to. Okay, and you have to also decide this cap so that your phase field in turn grows into 1 for that history field. Otherwise, you will see all kinds of spurious cracks. Okay, so h only ever increases, cracks never heal, which is the irreversibility case. And this is, as I said before, this is one of the main assumptions of the phase field model, which we have to ensure. Now, we have the GTN porosity F. We define the history field using this F. And using this history field, we calculate the phase field and we plot that contour in order to give us the crack. I hope this coupling part is clear. Now, how do we run this in Abacus or a commercial finite element software? I use Abacus. Okay. So, the phase field equation needs to be solved across the whole mesh, coupled between elements. Standard approaches use special user elements, VUEL, which is complex and hard to parallelize. Okay. So, if you look at different research papers, you will find that the most common part or the most common approach to do this is a VUMAT plus VUEL approach. VUEL is what? It is a vectorized user element subroutine, and VUMAT is a vectorized user material subroutine. Okay. So using the VUMAT, you define your entire GTN model and your history field and stuff like that, your stresses and stuff like that. And using the VUEL, you define the shape functions and all element details of the phase field model itself. Okay, so using the VUEL, you define the phase field element itself, and then you exchange the history field between the VUMAT and the VUEL. That is basically how you do it. But the main issue between that is that it takes a lot of time to complete. In an explicit format, if you have a very fine mesh, it will take a lot of time to complete. Okay, so what you do, you parallelize or you use parallel computing, you use multiple CPUs. Okay, but using this VUEL, there has been a lot of problems. I personally have also faced that. There has been a lot of problems in order to use multiple CPUs. Okay, like VARS module and stuff like that, where you use parallel computing, but it takes a lot of time. It is complex. So what you do is you follow another path. The trick is the phase field equation has exactly the same form as the heat conduction equation. So we let Abaqus's built-in thermal solver do the work. The temperature becomes the phase field. Okay. So what is the heat conduction equation? The heat conduction equation is this: rho Cp T dot minus kappa nabla square T equals to the heat flux Q. So here, if you compare the dynamic phase field equation, let me go back. If you compare this equation, you see that equation had a T dot. This equation has a D dot. Okay, that had a nabla square T. This has a nabla square D. Okay, and that had a Q term. This has this term, this entire term to the right of the equal sign. That had a rho Cp. This had a E. This has a eta. Okay. So we define that analogous equation, which is this, and we try to calculate using Abaqus's built-in thermal solver. So Abaqus has a built-in thermal solver. Okay. So we try to use that. So we have the same mathematics. We reuse a solver that already runs on many CPUs. Here we don't have any issue regarding parallelization. Okay, it will run on multiple CPUs built in. We don't have to define using VARS module or something like that. So the thermal analogy: each thermal quantity is reinterpreted as a phase field quantity. Okay, so T becomes D. So temperature becomes phase field. Rho Cp becomes eta. So the heat capacity becomes viscosity. Kappa becomes Lc square. So conductivity becomes length scale square. And this entire term, the heat source term Q, becomes the crack driving term containing the history field. Okay. So we set thermal expansion alpha T equals to 0. This is the coefficient of thermal expansion. It should be subscript T, but yeah, this is the coefficient of thermal expansion and this should be 0. The temperature degree of freedom is the phase field. It is not real heat. Correct? Because we are just substituting. We are just finding an analogous equation. So this is not real heat. So we use two subroutines with one model. We use a VUMAT, which defines the material or the mechanics, as I was saying. So it computes stress from strain, the GTN return mapping. It updates porosity F, so growth and nucleation. It builds the crack driving force, the history field H from F. And it applies the degradation G of D and deletes failed elements. So essentially what we have to use element deletion in these kind of simulations. Why? Because whenever your history field reaches infinite, or whenever your F reaches FF, the stress carrying capacity of that particular element becomes huge. Okay. So what I use is I use a stress degradation. So what I do is when F reaches FF, I take that element with F equals to FF and I degrade its stress drastically, so that the effective stress of that element after failure, it becomes close to 0. Okay, but again, if the stress carrying capacity of a particular element goes to 0, no matter how small loading you apply, the element will distort very, very high. So it is very, very important to delete those elements from the mesh. So this is what is meant by deleting failed elements. So elements, I'm repeating again, elements with zero stress carrying capacity have essentially failed, right? So elements with F equals to FF have essentially failed, and those elements need to be deleted from the mesh. And this is where we use element deletion. It obviously has a lot of jargons, but again, this is the most ideal case to use element deletion when F equals to FF. You can always use your own criterias, but again, the most basic format is to use when F equals to FF. Okay. And on the other hand, we have a VHETVAL formulation. This VHETVAL formulation is the temperature formulation where essentially the heat source is the phase field. So here the input is only the heat source and the output is the temperature. This is the you can always check the Abacus documentation for this subroutine, but again, the input is the heat source and the output is the temperature. Here for us it is the phase field. Okay, so it reads H stored by the VUMAT. How? It reads H using the heat source term Q. Okay, it supplies the heat source Q to the thermal solver. The thermal solver evolves D across the mesh, and this runs natively on multiple CPUs because there is no user element involved here. Okay, this is one of the major reasons that why we use a VHETVAL instead of a VUEL. Okay, it's important. In the next video, I will discuss snippets of the code, so you will be able to understand exactly what I am doing. So, what VHETVAL returns? The heat source and its derivative. This is the entire phase field physics in one line. Okay, so what? It returns, it takes in the heat source and its derivative, and it returns the phase field or the temperature. So this is how the heat source is defined, and this is the derivative of the heat source with respect to phase field. Okay, so it will take these two into account, and at equilibrium the phase field settles at this. So this is the analytical expression of the phase field with respect to the history field and GCN LC. Okay, so this is what you use in one-dimensional cases typically, but again, this is internally how the VHETVAL solves for the phase field. Okay, so a larger driving force H pushes D closer to 1, which is fully broken. Okay, so you can understand when F goes to FF, according to that history field equation, H tends to infinity, right? So when H tends to infinity, what happens? Your phase field also goes to infinity, or it is undetermined. So it is very, very important to cap. It is very, very important to cap H until you get your effective phase field as 1. Because beyond 1, phase field cannot grow, right? So inside the VUMAT solving for stress, so each increment, the GTN yield condition is solved with a Newton return mapping. So there are two unknowns, the plastic multiplier and the pressure. So if you remember from the previous video, you always have a plastic multiplier to define your equivalent plastic strain. Okay, so that is one unknown that you have to find out. And also, if you see the yield function of the GTN model, you will see that there was a pressure term. Okay, so that pressure term is also unknown in the equation. Okay, so you define your Newton return mapping like this. You have increments of the plastic multiplier and you have increments of pressure. You have a Jacobian inverse into residuals of R1 and R2 defined by, all of your stress, strain, thermal parameters. Okay. So the first step is the elastic trial, which is to predict stress assuming no new plasticity. So initially the material will be elastic, right? When you start to load it, it will be elastic. There will not be any plasticity. So that is our elastic trial strain or our trial stress. Next, we have to check yield. So is the GTN surface violated? If you remember again, when your yield function or your plasticity yield function is greater than 0, that is when plasticity evolves. Okay. So that is when you use the return map, this Newton return mapping. So we iterate to bring stress back to the surface. So essentially what? Essentially phi should be always equals to 0 in order to get a critical condition of plasticity. So when phi is greater than 0, we use this Newton mapping in order to bring that phi from greater than 0 to equals to 0. Okay, this is how the return mapping works. We iterate in order to bring stress back to the surface. And we update damage, we grow porosity, we build the history field, we degrade and we delete elements. Okay, so this is what the VUMAT follows. So the complete picture, we have the phase field D, a smooth crack variable from 0 to 1. Then energy driven, where the cracks grow to minimize total energy, as you know. Then we couple it with the GTN. So porosity F feeds the driving force H. Then we apply the thermal analogy, where the phase field is solved as a heat problem. Next, we use this VUMAT plus VHETVAL formulation, where mechanics and crack split across two subroutines, which essentially exchanges the history field amongst each other. Okay. And lastly, this runs on multiple CPUs. So there is no user element. It is natively parallel. Okay. So from tiny voids to a full fracture simulation, we have a entire model that we can now code and we can calculate porosity and phase field cracks form. Okay. So in the next video, I will talk about the entire code. I will show some snippets. I'll talk about algorithms, and that will be a longer video. Okay, I hope this video was clear. So thanks for watching.